All right, so welcome back, everybody. Today we're going to finish up our lecture on Gauss's Law, which we started on Monday. So we introduced the idea behind Gauss's Law, and it has to do with this thing called electric flux. So we know how to do the various calculations that go into using Gauss's Law. But what we're going to try to do today is just go through many examples of how to apply it. So we're going to start with a bunch of examples where we're using Gauss's law to calculate an actual value for an electric field or a formula for an electric field in a certain situation. And then towards the end, we'll look at some other applications besides just calculating E fields. Okay? But to get back into the lecture, this is where we left off. In this example, we have a non-conducting sphere. So we're trying to use Gauss's law to calculate what the electric field due to this sphere actually is. So here's the situation. A spherical non-conductor of radius r has a net charge q uniformly distributed over its volume. So this is different from the example we ended on last time. Because in the last example we did, we said the charge on a conductor was uniformly distributed over the outer surface. Okay, but here, the charge is distributed over the entire volume. So there's actually charge on the interior of this thing, okay? So that's the difference. So just like before, we're going to find the electric field as a function of R, or a formula for the electric field as a function of R, which is distance from the center. Okay, so we're going to split this into two parts, okay? First, we're going to apply Gauss's law to this surface shown here, surface number 1. And basically what this is a spherical shell, radius little r, where little r is smaller than capital R. So in other words, we're just inside of this sphere, okay? We're on the interior of the sphere, and we want to know what the electric field looks like when we're on the interior of the sphere, okay? So we'll work that out, and then we'll do it again for the outside of the sphere. Okay, so now we're going to work this out on pen and paper, so follow along with this. Okay, so here's what we are trying to do. We're trying to apply Gauss's law to surface number 1, which is a spherical shell that has radius lowercase r, okay? And that lowercase r is less than big R, meaning we're inside. Okay, so if we apply Gauss's law, we're going to have to deal with this equation. Integral E dot dA. So what is this? This is the electric flux through the surface that we chose. That equals Q enclosed, so that's how much charge are we surrounding with our surface, divided by epsilon naught. So the typical approach when you're doing Gauss's law is just to evaluate separately these two pieces. So first, I'm going to work out this E dot dA thing, and then I'm going to work out the Q enclosed, and then I'll just put it all together at the end to solve for E. Does that make sense? So we're going to do those two separately. Okay. So let's tackle the enclosed charge. Okay, so for this sphere, the charge on it is uniformly distributed over the volume. So it's evenly spread out over the entire volume of the sphere. And one way we can express that idea mathematically is to say, rho, that's our charge density, charge per unit volume, is a constant. So the sphere that contains all this charge has the same density of charge everywhere. Okay? It's not varying from place to place. It's just the same density of charge everywhere. Does that make sense? And this comes from the fact that charge is uniformly distributed. Okay, so that's why we were able to write this down. Okay, so what is the definition of rho as an equation?
L over V.
So that would be if we were talking about mass density, but this is charge density, so it's Q over V, right? It's charge per unit volume. So I could take this to be the total charge on the entire sphere divided by the total volume of the entire sphere. That's one way I could express the density of charge. But another way I could do it is to say, this is the charge that we're enclosing with our surface divided by the volume we're enclosing with our surface. And the idea is, because the density of charge is the same everywhere, regardless of how we calculate it, if we choose the whole sphere or just some part of it, we're going to end up with the same answer. That's why we were able to do this. Does that make sense? Okay, so the total charge right here is just Q, right? That's what we're calling the total charge. How can I express the total volume? What would be a formula for that? So we're talking about the volume of a sphere now, right?
4 pi r squared.
It's, okay, not area, but volume.
3/4 pi r cubed.
It's 4/3 pi, and then for the total volume, I would use big R and cube it, okay? That's the total volume on the entire sphere. And again, we're saying that should equal the charge enclosed divided by the volume enclosed. That's just another sphere, it's just a smaller one, right? This one has radius little r, right? So this is same formula but different r value. Does that make sense? Okay, so let's just drop the 4/3 pi. And then let's solve for Q enclosed. That's what we're trying to do here. We're using Gauss's law. We want some kind of expression for Q enclosed. So that is little r to the third divided by big R to the third times the total charge Q. And again, just to reiterate, what we're showing is if we have the overall volume of the sphere, okay, that radius is big R, but the smaller volume that we're enclosing is little r, and what we're saying is the amount of charge here in the smaller volume is this ratio of the r values cubed times the total charge, okay? And we work that out by assuming the charge is uniformly spread out. Make sense? Okay, so let's do the other piece of this. Let's do the integral of E dot dA. All right, well, one thing to note as we go through these examples is we have a spherically symmetric field in this case. And the integral E dot dA for a spherically symmetric field always just works out the same way. But let's just go through the exercise again, okay? So we have a spherically symmetric E field. That means the E field lines are just radiating outwards in all directions. And then our surface that these E field lines are going through, again, is a sphere of radius small r. So my E field vector pointing this way, and my dA vector, remember that's perpendicular to the surface, that's also going radially outwards, okay? That means when I take the dot product of E and dA, remember how all dot products work, take the magnitude of the first vector times the magnitude of the second vector, which is dA, and then we take cosine of the angle between them, but you can see they're pointing in the same direction. So what would the angle be between the two vectors? 0, which just gives you 1. And then another thing to remember is that because our electric field strength, the magnitude E, only depends on how far away we are from the center, it's going to have the same value everywhere along this surface, okay? Because everywhere along the surface we're the same distance away from the center. So because the strength of the E field is the same everywhere on the surface, it's something we can pull out in this integral where we're integrating over the surface, treat it as a constant. And again, we have to be able to do this in Gauss's law if we want any hope of solving for the E field. So pulling it out of the integral is an important step, okay? Okay, then we have the strength of the E field times integrate over the dA vectors, or the dA areas, right? But that just gives us the total area of this surface. So now we're talking about the surface of a sphere. Surface area of a sphere. What's the formula for that? This is 4 pi r squared. So when you're using Gauss's law, you really got to keep straight in your head the difference between volumes and areas. It's especially with the spherical case, it's easy to get these mixed up. So the surface area is 4 pi r squared, and that's different from the volume. Okay. All right. So now we have all the pieces that go into Gauss's law, right? We have E dot dA and we have Q enclosed. So now let's just put it together. For E dot dA, we have E times 4 pi r squared. And then we have 1 over epsilon naught, that's here. I'm just going to put it out front. And then our Q enclosed, we said, was, okay, small r to the third divided by big R to the third times Q, which is the total charge. So now we solve for E just by dividing out this part right here. So to collect all the terms, what do I have? I've got a Q on the top, and then I have a 4 pi epsilon naught on the bottom, and then I have a big R cubed on the bottom. But as far as small r is concerned, what factor do I have? What power? Just to the first power, right? Because I have r cubed divided by r squared, just r to the first power. So notice something. This is a different type of E field that we haven't seen before. It's actually growing linearly with radius. It's not falling off with radius. It's getting bigger and bigger as you go out, okay? So we see how this works? All right, so let's put that up on the slide. So we did this, and we found that the strength of the E field inside of the sphere is given by a Q little r divided by 4 pi epsilon naught big R cubed. And so all of this stuff here can be considered constant. And what it's telling us is that as long as you're inside of this sphere, the E field is getting stronger and stronger as you go further out from the center. Okay? It grows in proportion to R. All right, so then the logical next step is to apply Gauss's law outside of the sphere. So again, this is a general thing we'll have to do. If we're inside of the charge distribution, we'll have to apply Gauss's law for that case. And then if we're outside of it, we'll have to apply Gauss's law again for this other case. Okay, so now our Gaussian surface is bigger in radius than our charged sphere. And we'll see what we get in this case, all right? So we're going to go through the whole thing on paper, but it turns out this will be a simpler calculation. So can anyone tell me, for this second surface, what is my enclosed charge?
Q.
It's just Q, and it doesn't depend on anything else. As long as I'm outside of the charge distribution, I'm just enclosing the entire thing. It's a different story when we're inside, right? The amount of charge I'm enclosing depends on how far out I go, but as long as we're out here, the charge I'm enclosing is just the total charge Q. Make sense? Okay. So therefore, for surface number 2, now we have a spherical shell just like before, but now we're outside of our charge distribution. We can say Q enclosed is just equal to Q. And the E dot dA part works out exactly the same way because we still have a spherically symmetric E field. So I could go through all of this again, but I'm not going to. It's the same exact statement as before, okay? So we have integral E dot dA equaling, skip the work because we did it, E times 4 pi r squared. That fact hasn't changed. Okay? So now let's put it together in Gauss's law. We have integral E dot dA, okay, which works out to E times 4 pi r squared. That equals Q enclosed, which in this case is just Q, divided by epsilon naught. So therefore E, the magnitude of the E field, is Q divided by 4 pi epsilon naught r squared. So this should look familiar too, right? That just looks like Coulomb's law. And again, I think I mentioned this at the end of the last lecture, but if we have a spherically symmetric distribution of charge like this, and we're outside of it, the E field it creates just looks like a point charge, which is given by Coulomb's law. Okay? That's just a general result we'll keep seeing if we work out problems like this. Any questions on this second part? Okay, so to summarize, when we applied Gauss's law to the second surface, we got this. Q over 4 pi epsilon naught r squared. So now the E field is getting weaker with distance, right? Because it's a 1 over r squared thing. That makes sense. We're just literally getting further and further out from the charge. And that's how it works. Okay, so like before, what we're going to do is plot this out. Okay, so when it came to the E field, in solving for the E field, we found these two different results that apply to whether you're inside the sphere or outside the sphere. Okay? And what we saw was inside the sphere, the electric field strength is just directly proportional to your radius. So if I start from the center, my E field strength is 0, because you can see how if you were to plug in 0 for R, E would equal 0, right? But as I get further and further out, it increases. So what I'm showing you here is a linear increase in the E field strength as long as we're inside. But then, as soon as we are outside the sphere, now it follows this relationship, where it's a 1 over r squared sort of thing. So it linearly increases to some maximum strength when you're right at the edge. And then as soon as you go outside, it starts falling off like an inverse square law. Okay? So any questions on how we arrived at this?
It's not really a question about like equations and everything. It's just like when you say non-conducting sphere, is that like, would it be the same if it were a conducting sphere? Like what?
Okay, so
is it relevant right now?
yeah, okay, yeah. Thanks for asking that. We're going to actually address this at the very end. But the idea is, if you have a conductor, all of the charge tends to spread out on the outside of it, and none of the charge is on the interior. And a non-conductor, the charge can just fill out the whole volume. But we haven't shown that yet. We're going to show that at the end of the lecture, because we're going to work our way up to it. For now, we're just kind of taking it as a fact. Okay? All right. So we'll keep it moving. All right, so now I'm going to up the complexity a little bit more. Okay, so it's the same idea. We have a sphere, radius big R, and it has some charge inside of it, right? The charge is filling out the volume. But this time, it's not uniformly distributed. Okay? So, can someone close the door to the outside? There's just a lot of noise going on out there. Thank you. Appreciate it. Okay, so this time, our charge density is not uniform anymore. So instead, it's going to be given by a function. Now, this is generally something you have to deal with if you have a non-uniform charge density. It's not enough to just say it's non-uniform. You need to describe exactly how it's non-uniform, which means you have to give some kind of function that describes what the charge density actually is. So we have to be given some function to go any further. So let's just work with this one as an example, okay? Let's suppose that the charge density as a function of radius is given by rho naught times little r squared divided by big R squared, where rho naught, just treat that as a constant, and big R, of course, we treat that as a constant. So let's actually just examine this a little bit more closely. If I were to plug in 0 for little r, what would I get out? I get 0. So that's telling me at the very center, the charge density is 0, right? But as r increases, the charge density also increases. So we get a more and more dense clustering of charge as we go out. That's what's being shown here. Does that make sense? Okay. So in this case, here's what we're dealing with. The strategy is mostly the same, but as we'll see, the details kind of change now. First, we're going to apply Gauss's law to this first surface, which again is a spherical shell, which is inside of this charged sphere. Okay? So let's work it out for that first case. And we'll do that on paper. Okay. So we're doing surface number 1, right? And that's the one where we're inside the sphere. And the charge is not uniformly distributed, so we can't use the same strategy as before to come up with a formula for Q enclosed. We have to do something else, and I'll show you what that is. But remember, the broad outline of what we're doing is we have Gauss's law, which says E dot dA equals Q enclosed over epsilon naught. And essentially, we need to work out both sides of the equation, and then we can solve for E after we do that. So because we still have a spherically symmetric field, the E dot dA part works out exactly the same as before. Okay, so you've seen the work as to how to do this, but just in the interest of saving some time, I'm going to just skip right to the result. We know that in a case like this, E dot dA is going to work out to E times 4 pi r squared. Okay, so just using the result we showed earlier. Okay, now let's work out Q enclosed. Let's finally get to that. So here's what I'm going to do. I'm going to write down an expression for the charge density rho. And remember, this is charge per unit volume, correct? But I'm going to write this in differential form as dq divided by dv. Because it's non-uniform, I have to take this sort of approach. And what I can do with that is sort of rearrange it to say dq, some tiny element of the overall charge, is equal to the charge density rho times some volume dv. Okay? So what am I going to put in for rho? I'm not going to treat it as a constant anymore, right? Instead, I have to use the function that we were given. Okay? So what was that function we were given? It was rho equals rho naught times small r squared over big R squared. So that's going to go in here. What about dv? Any ideas for that? This is what we call a volume element inside of an integral. And since we're dealing with a spherical type of geometry, there's a certain way to express this. All right, I'll show you how to work this out, okay? Let's start with this. What's the volume of the sphere again? 4/3 pi r cubed. Okay, so if I were to take the derivative on both sides, I could write this as dv equals something times dr, right? By just taking this derivative. What's the derivative here? Yeah, 3 comes down, cancels this 3. And then the power is reduced by 1, so it's now 2. So we have 4 pi r squared dr. So if you have a tiny element of volume within some kind of spherical distribution, this is generally what dv works out to. Okay? So you may have seen this before, but that's how we get there. Let's actually take a closer look at this and try to interpret it, okay? So, you know, this part kind of looks familiar. That's the area on the surface of the sphere, right? And then dr is like a tiny thickness, basically. So the way to picture this, to picture what this formula is saying, imagine we have a sphere, but it's kind of like a thin shell of a sphere, where the radius is r, and the thickness of it is dr. So the volume on this very, very thin shell, which I'll kind of fill out here, would just be the area, which is 4 pi r squared times the thickness. So I'm just showing you how to interpret this equation, okay? Just how to visualize it. So we can think of the overall spherical volume as being constructed from these tiny little shells. And of course, if we integrate over all the shells, we'll get the whole volume, okay? Okay, so with that said, I'm going to take this expression for rho, this one right here, and this one for dV, and plug it into the dq. So we have dq equals rho, which is rho naught times r squared over big R squared, multiplied by 4 pi r squared dr. And just to clean this up a little bit, I'm just going to pull out everything that's constant for convenience. So we have 4 pi, we have rho naught, and then we have big R squared on the bottom. And then we have small r to the 4th power from here and here times dr. So what is this telling me? This dq is a tiny element of charge contained within this tiny element of volume. If I want the overall charge, that's what I'm trying to get here. I'm trying to find the overall charge. I need to integrate this thing, okay? So if you have a non-uniform distribution of charge, the only way to get Q enclosed is to integrate. That's what I'm telling you here, okay? So Q enclosed would be the integral over all my little dq elements, starting from the center all the way out to the radius of my surface, okay? And so right away I'm going to pull out what's constant because we already made a note of that. And then I have the integral of r to the 4th dr, which is not too bad, right? Okay, so here's what I'll do. Remember, I want the total charge enclosed by my Gaussian surface. So that means I'm going to start at radius 0, and I'm going to go out to radius small r. That's the radius of my Gaussian surface, okay? So 0 to small r. All right, so what does this integral work out to? We have, so we're integrating, so we increase the power by 1 and then divide by that power we get, which is 5, okay? So now we have 4 pi rho naught divided by big R squared times 1/5, r to the 5th, and we evaluate from 0 to r. And of course, if we plug in 0 into this guy, we get 0 back, right? So this is just 4 pi rho naught over big R squared, and then we'll put this 5 down here, and then we have r to the 5th minus 0 to the 5th, so that's our enclosed charge. So we have to integrate over the charge density to get that enclosed charge, okay? But now that we have it, we can do the rest. Because we're just going to directly apply Gauss's law. We have the E dot dA part, and now we have the Q enclosed part, and that was a little more work than we've seen before, but we have it so we can now just plug it into the formula and go from there, okay? So for E dot dA, recall I have D times 4 pi small r squared, and then I have Q enclosed over epsilon naught. My Q enclosed expression is already kind of messy, so I'm just going to write 1 over epsilon naught out in the front.
Can you scoot the paper up a little bit?
Sorry, 1 over epsilon naught in the front. Okay, so this is what I was writing down. And then I'm going to put in my Q enclosed expression. So that's 4 pi rho naught divided by 5 big R squared on the bottom, and then small r to the 5th on top. So this is something we can simplify a little bit. E, okay, 4 pi factors cancel, right? I have a rho naught factor on the top. I have a 5 on the bottom. And I have a big R squared on the bottom as well. And then as far as small r is concerned, what factor do I have?
R cubed on top.
I have r cubed on top, right? Because I have r to the 5th, and then I divide out r squared. So this is the expression for the E field as long as we're inside of this charged sphere. Okay? Any questions on how we got that?
No questions, but can I have it up for a little bit, just to see?
Okay. I'll leave this here for just a second. And actually, you can probably tell what is going to happen next, right? So this is the formula for the E field as long as we're inside the sphere. Now we have to evaluate for outside the sphere, okay? What can I say about the enclosed charge? This whole kind of calculation we did here, if we're outside of the sphere. What would be different about this step if we're now outside of the sphere? So my top limit, if you think about it, would now be big R. Because if I want the entire charge on the whole sphere, I'd go from the center all the way to the edge of the sphere. But then after that, there's nothing, right? So I just go from 0 to big R in this integral. That's what would change. Does that make sense? Okay.
And that would be the charge outside.
Yeah, so that would be the total charge we're enclosing if we're thinking of a surface that's on the outside. Yeah. So here, let's summarize the first result, which is basically the E field depends on R cubed, okay? So that's just the formula we got earlier. So now, to answer your question, here's what we're going to do. We're going to apply Gauss's law to this second surface, which is outside of the sphere. And what I was saying is, if we want to know the total charge enclosed here, that's just the total charge contained on the sphere. So if we're calculating that charge by integration, we would start at 0, and then we go all the way out to big R. That would give me the entire charge on the sphere. Okay? So that's what we'll do next.
I have a question.
Yeah.
Why wouldn't it be from the edge of the sphere to the inside of the? Why wouldn't it be from big R to little r?
Because with this surface, so you would be leaving off this charge if you did that. I want the whole thing. So I want to go from the center all the way to the outside to include the whole charge on the whole thing.
So, but couldn't you just start with that right there, what we did the first time? And just expand it, or no?
I'm not sure what you mean, but like,
Because we already did the first part, right? The inside of it.
yeah.
So couldn't you just keep going from there?
Yeah, we'll use some of the same formulas we already developed. It's just we're gonna, like I said, we're gonna integrate from here to here. We're just changing the limits of integration. So we set up how the integral works. We're just changing the limits. Okay. Okay. So now, for surface number 2, which has small r greater than big R, where we're outside. Okay, what I'm saying is we're enclosing the entire charge. That's on the sphere. Okay? So for Q enclosed, here's what I'm going to do. I'm not going to work it out all the way from the beginning. I'm just going to start right there. Okay? Where we have 4 pi times rho naught divided by big R squared. And then we had a 5th times r to the 5th. And here's where I'm changing the limits. Okay? This now goes from 0 to big R. So now we're including every single bit of charge on the sphere, not just some of it. Okay? Does that make sense? So I have 4 pi I have rho naught divided by big R squared. The 1/5 factor I'll just bring down here with this term. And then I'll have big R to the 5th power as my top limit, and then just minus 0 for my bottom. So this is an expression for the entire charge on the whole sphere. Which, to simplify, what factor of big R do we have overall? 3. R to the 3rd. Okay? Does that make sense? So now we'll apply Gauss's law once again. Okay? What does Gauss's law say? Integral E dot dA, which we already know what's put in for this because we have a spherically symmetric E field. That equals Q enclosed, which is the new expression we just developed, divided by epsilon naught. Okay, so that's what we're doing now. So the E dot dA part worked out to E times 4 pi little r squared. That's what we had. But that equals 1 over epsilon naught times this guy. And notice that this is just a constant, right? As long as we're outside of the sphere, we're enclosing the same amount of charge. Doesn't matter if we're really, really far out or just above the surface. As long as we're outside of it, we're just enclosing some constant amount of charge. And that's what's being reflected here. So we have 4 pi rho naught big R to the 3rd on top divided by 5. And what that works out to is E. Okay, we can take the 4 pi factors and cancel those out, right? So we have rho naught on top, we have big R to the 3rd on top, we have 5 epsilon naught on the bottom. And now we have R squared, small r squared on the bottom, okay? So that's certainly a valid answer. But let me just show you one other way to think about this, okay? Just going back to this step, I could have also written this as E dot dA works out to E times 4 pi r squared. But then my enclosed charge, I could just write this as Q total, whatever the total charge on that sphere is, right? Because I'm enclosing the whole thing. So this is a valid way to write it. And then we see that when we solve for E in this case, we get Coulomb's law back. Q total over 4 pi epsilon naught r squared. So these are just different ways of saying the same thing. It's a 1 over r squared dependence. It's just how we write the constants in front. Okay? And this way is just instructive because it tells you that it follows Coulomb's law. Okay? So, we're good on this? Okay. Let's go back to the slide to summarize. So this is what we had for the second surface, rho naught times big R cubed over 5 epsilon naught little r squared, which, as we said, can alternatively be written as the total charge, Q total, divided by 4 pi epsilon naught r squared on the bottom, which, again, is showing us it behaves just like a point charge as long as we're outside of the charge distribution. Okay, remember I said that's something that's going to keep popping up in these cases. It's happening here too. Okay, so the next thing we're going to do is kind of a process that hopefully you're seeing in these examples. We're going to just plot what it looks like on a graph. Okay, so we're going to have electric field going this way and radius going this way. And we'll just see what it looks like qualitatively. All right? Any questions? All right, so in this particular example, again, we have these two different expressions. One is valid on the inside, and the other is valid on the outside of the sphere. Just to get a sense of, what the shape of the graph looks like. When we're inside of the sphere, now the E field increases according to r cubed. So, same as before, if we're right at the center, where r is equal to 0, we have 0 E field. But it gets stronger and stronger as we go out, and then it increases as r to the 3rd power, as opposed to r to the 1st power like last time. So the r cubed, might look something like that. But then as soon as we're outside, and we keep going out, now the E field is decreasing in strength according to 1 over r squared. So follows an r cubed relationship inside the sphere and then a 1 over r squared relationship outside. So that's roughly what it would look like when you plot it out. Okay?
Do you
All
always
right.
go based off of like little r, of like what type of graph it should look like?
Yeah, because little r in these calculations, we're taking that to mean how far away from the center are we calculating the E field. Okay? So that's what it's meant to mean in these calculations. Anything else?
So this graph works because of the given rho, right?
Yeah, so it's all because of the given rho function. If I gave you a different type of function, which is going to happen on upcoming homework assignments, it will work out differently. So if you have a non-uniform charge distribution, I need to give you the rho function to tell you exactly how is it non-uniform. Okay? All right, so we did a whole bunch of spheres. I think you know, there are more examples you can think of with spheres. But let's move on to something else, okay? Because maybe you're getting bored with spheres. Let's do cylindrical symmetry, okay? So the simplest case is an infinitely long line of charge. So that's what we're dealing with here. You have an infinitely long line of charge, and the linear charge density, remember this means charge per unit length along the line, it's going to be given by lambda. So what we want to do is find an expression for the strength of the electric field as a function of your distance from the line. Okay? And do you remember we did this problem back in the first chapter, right? We did it in lecture, and we also did it in lab, if you recall. And if you recall, that wasn't such an easy problem, right? It took a while to set up the integral, and the integral itself was pretty difficult to actually evaluate, right? In this case, it's going to be a lot simpler. This is one of these cases where Gauss's law is clearly the preferred method to calculate the E field, okay? So let's explain how we're going to do this. Okay, this type of E field, when we have a line of charge, is going to be cylindrically symmetric. So that means it basically only depends on your distance from the line. And if you rotate the line, it's going to still appear the same. So what that looks like is the E field lines just going outwards away from the line in all directions. Okay, that's our cylindrically symmetric E field. Okay, so we went over this last time, just reminding you. So the E field lines are pointing out away from the line. So we want to apply Gauss's law, and guess what that means? We need to construct a surface that encloses the line of charge and has these E field lines going through it. Okay? So can you guess what type of shape I could sort of draw here to evaluate this using Gauss's law? Yeah, it's going to be a cylinder, right? You have spherical symmetry, you use a sphere. You have cylindrical symmetry, you use a cylinder. So here's what that looks like. So just keep in mind, the line itself extends, infinitely far in both directions. That's what we're just assuming here for this problem. But the cylinder that I draw, that's going to be finite, okay? So I'm only really putting it on top of some piece of the line, not the whole thing, okay? And what this surface is a cylindrical shell. For the radius of the shell, we're going to call that small r. So that would be your distance from the line out to where your cylinder is. And then the length, which would be the length of the cylinder, we're calling that L. All right? That's our surface. So let me ask you this. The surface kind of has three parts to it, if you think about it. You have like this circular end cap, this circular end cap, and then sort of the curved outer surface of it, right? Only one of those parts has any E field lines going through it. Which one is that?
The cylindrical part?
It's only this curved part that has any E field lines going through it. There are no E field lines going out the end caps. Do we see that? So in other words, if I'm trying to think about the flux through this surface, I don't need to include the end caps because there are no E field lines going through those end caps. Is that clear?
Does it matter is that because it's infinitely long, or if it was a finite length?
Yeah,
or
so
there's still
if this had an endpoint to it, this would break down. So we can really only evaluate things that are either infinitely long or long enough that we can treat them as infinitely long. So yeah. So in other words, you're just really far away from wherever the ends might be. And this is perfectly valid, by the way, in a lot of real-world situations. Like, let's say you have a really long wire that has some charge on it. This would work pretty well. Okay. So let's work it out. So I'm going to draw that same surface, maybe from a slightly different perspective. So this dashed line, that represents our line of charge. And then here is our cylindrical surface. It's completely centered around the line. And remember, we have E field lines just pointing directly away from the line, radiating in all directions. I'm just going to draw one of those E field lines. Let's say this one. All right. And just remember, we don't have any E field lines going through these circular end caps. So I'm really only concentrating now on the curved part. So how does my dA vector point for this surface? It's perpendicular to the surface, and it's pointing outwards, remember? It's pointing out, away from the surface like this. So that's my dA vector. So the nice thing about my dA vector is it points in the same direction as my E field, right? My E field is coming radially out, and so is my dA vector. That's very convenient for us, okay? Because when we evaluate the integral E dot dA for this closed surface that I constructed, here's what we'll get. So I'm just going to make a note that there's no flux through the circular end caps. If there were, we'd have to have some other terms here, but I'm just considering the curved part. Okay, so for the curved part, we have E, the magnitude of that vector times dA, the magnitude of that vector times cosine of the angle between them, which is 0. So if we have a nice symmetry, that's typically going to be the case. Okay, the other thing we can note, so take this work and put it down here, is that all over the curved part of this cylinder, the E field has the same strength. Because the E field only depends on how far away from the line of charge you are. And at all points on that cylinder, we're the same distance away from the line, right? So, therefore, E can be pulled out as a constant. And then the cosine 0 just goes to 1, so I left that alone. So now we have E times integral over all the dAs, but that's just the total area of the curved part. Does anyone know the formula for the area of the curved part of a cylinder? You know where that comes from? Yeah, so here, let's say this is my cylinder. Okay, so I'm going to take just a sheet of paper and roll it into a cylinder. And again, we only care about this area, not the circular end caps. Okay? So this would be the circumference, correct? And then this would be the length. So if I were to unroll it into the sheet again, that was the circumference, and that was the length L. And then what's the formula for the circumference? So this would be the 2 pi r distance, and this would be the L distance. So that's where that formula comes from. So to summarize, if we unravel the curved surface, it's going to look like this. It's going to look like a rectangular sheet where on one side we have the length L, and on the other side we have the circumference 2 pi r. So this total area is 2 pi r L, as you said. Okay, so going back here, the electric flux through this surface then is E times 2 pi times r times L. Do we agree? And by the way, much like for the sphere, how the E dot dA kept coming out to the same expression, whenever we have cylindrical symmetry, this is the relevant expression for E dot dA. It's always going to work out to this. It's the Q enclosed part that's going to change depending on the situation, okay? So, okay, let's tackle that actually, because the idea, as always, is we want to evaluate both sides of Gauss's law, the E dot dA part and the Q enclosed part. So we've successfully done that. Let's now think about Q enclosed, okay? Okay, lambda. This is what we call our linear charge density. I just want to remind you of what this thing means. It's the charge per unit length on the line. Okay, and now let's think about how that applies to this picture here, right? So depending on how long we draw this cylinder, we might be enclosing more or less charge, right? So if I draw a really short cylinder, that's not enclosing as much charge as a longer one, right? Because it's just covering more of the line. But lambda should just be whatever charge I happen to be enclosing with this thing divided by the length of the cylinder, right? Does that make sense? So that means the charge I am enclosing, just lambda times L, okay? Go ahead. It doesn't really matter because this is perfectly uniform. Yeah. So if this were non-uniform, we'd have to treat it as an infinitesimal, then integrate. But in this case, we do not have to do that. Okay. So here, Gauss's law. I'm just going to write it down. E dot dA equals Q enclosed divided by epsilon naught. For the E dot dA part, we got E times 2 pi times RL. For the Q enclosed, we got lambda times L, and then we're dividing epsilon naught. So therefore, E is equal to, cancel out the L factor, and by the way, it makes sense that L should cancel out, because we know that at the end of the day, the field should only depend on your distance from the line, not the length of some imaginary surface that we made up, right? So the L's cancel as expected. Then we have lambda divided by 2 pi epsilon naught times R. And I just want to remind you that K is equal to 1 over 4 pi epsilon naught. That's just another way of expressing the constant out front. So I could also, if I wanted to, write this as 2k lambda over R. And that would be the same thing. Okay? And this one should look familiar, right? This is what you worked out a few different times for, again, in the lecture and in the lab. And that is the formula for the electric field some distance away from a line of charge, an infinitely long line of charge, okay? And again, remember how just messy and tedious that was? I'm not saying this is the easiest thing in the world, but this would probably be the preferred method, right? Which way would you rather do it, this way or the old way?
This way.
Probably this way, right? So Gauss's law is nice when you can use it, but remember, you have to have a certain kind of symmetry to be able to use it in the first place. Okay? So any questions on this? All right, so that's an example using cylindrical symmetry. Sure thing. So that's an example with cylindrical symmetry. So we're going to do one more example with cylindrical symmetry. And do you remember the other type of symmetry we're going to deal with? Yeah, we're gonna have a planar symmetry as well. There's really only one example to do there, which is you have an infinite plane, right? That's pretty much it. So we'll do that next. But one more example with the cylinder, and then we'll get to the plane. All right. I'll leave this page at the front of the room if you need to come back to it later, okay, after class. All right, so here's what we came up with, and it's the same result that we got using Coulomb's law in the previous lecture, okay? All right, so any questions before we do the next example? Okay. So here's what we'll do in this next example. We have a non-conducting cylinder. So for our purposes, that means the charge is not just going to be on the outside of the cylinder, it's going to be all throughout the interior of it. Okay, and we'll explain why this is the case later. But for now, it just means the charge is distributed over the volume. Okay, so we have a long cylindrical non-conductor of radius big R. So radius big R is here to here. And it has a uniform volume charge density. What we're going to do is find an expression for the electric field as a function of small r, where small r is our distance from the center. So I just want to know, whatever distance I am from the center, I want to be able to calculate the E field, okay? Whatever that distance happens to be. So I will break this into two parts. And by the way, what we're showing here is just a small piece of the overall charged cylinder. You can imagine that it extends very far this way and very far that way also. We're just going to look at a piece of it for illustrative purposes. Okay? So the first thing we'll do, since we're applying Gauss's law, is we have to choose a surface. Okay? We know we have cylindrical symmetry. It's pretty straightforward that the surface should be a cylinder. But specifically, we want the cylinder that we use in Gauss's law to be smaller than the actual charged cylinder. Okay? And that means we're on the interior, we're on the inside of it. So we'll come up with some formula for what the electric field is inside of that cylinder. And then you can probably guess we'll do it again for the outside. Okay? All right, so this surface is just like before. It's a shell. The length of it is L, and the radius is small r. And yeah, I think that's all we need to know. So let's work it out. So going over to the paper now. Here's what we have. All right, so the first surface, surface number 1, is a cylinder where the radius of that cylinder, small r, is less than the radius of the actual charge distribution, which is capital R. Okay. So one thing that I already know is that the flux over the cylinder, that's the E dot dA part, the integral E dot dA. That's going to work out to E times 2 pi times R times L. I know that's the case because this electric field has cylindrical symmetry. Okay, so I worked this out for you before, but there's no need to go through it again because it works out in the exact same way. Okay, so let's just make a note. This is because E has cylindrical symmetry. Okay? I gotta move this over a little bit. Okay. So that means what we really need to work out is Q enclosed. Okay, that's what we want to come up with some kind of formula for. So in this case, the charge is uniformly distributed. Okay, and that's a simpler case. It means that basically rho, the charge per unit volume on our cylinder, is the same everywhere. So it doesn't matter if I take this section of the cylinder or another section, if I just take charge per unit volume, I'm always going to come up with the same answer. Okay, so that's what it means to be evenly spread out, is that the charge per unit volume is the same everywhere. So I guess we could say rho is constant, just like we did before. And then let's just come up with two different ways of expressing this, okay? So I guess one way we can express this is it's the charge that we enclose with our surface, Q enclosed, divided by the volume enclosed by our surface. That should be equal to rho. So if I want to take Q enclosed, solve for it, that would be rho times the volume we're enclosing with our surface. Make sense? So if rho is charge per unit volume, then the charge is rho times the volume. And rho is just a constant, so we don't need to do any sort of integral to work this out. Okay? So, what can I say about my volume enclosed? Now we have to think back to facts about geometry.
L pi r squared.
Yeah, we're talking now about the volume of a cylinder. Here, let's use this as our example, right? A cylinder is a shape that has a uniform cross-sectional area. It's a circular area, same cross-section as you go across it. So the area is pi r squared, and then if you multiply it by the length, that gives you the volume. Just like an area times length thing to get a volume. So the formula, let's just kind of do this on the side. V enclosed is the area times the length, which is pi r squared times L. So that means Q enclosed is just rho times that. So it's rho times the volume, which is pi r squared times L. Okay, we good on this? So next thing I'll do is I'll apply Gauss's law. And Gauss's law says the following. Integral E dot dA equals Q enclosed divided by epsilon naught. So we'll put in what we know for the flux on this side and for the enclosed charge on this side. So the flux, we have E times 2 pi times R times L. That's the flux through our surface. The charge enclosed by our surface is rho times pi r squared times L divided by epsilon naught. Okay? So that means our E field is the following. I can cancel out a factor of pi on both sides, so I'll do that. I'll divide out this 2, so I'll put it down here. So I'll have 2 epsilon naught on the bottom. I have a rho on top from this. And then notice my L factors cancel. So I canceled out pi and I canceled out L. And now we're just left with some power of R. What would that power be in this case?
Just R.
Yeah, so I have an R squared here. I have a single factor of R. So when I do R squared divided by R, just get R. So this is on the inside. What is that telling us? The E field on the inside of the sphere is actually getting bigger as you go further out from the center. But as we'll see, that's going to change once we go outside.
On the outside of the bigger.
Yeah, so you probably see where this is going, right? Yeah, you're correct.
No, I was gonna say we have to do the V enclosed, right?
For which part?
We have to do the V enclosed too, as well.
So we already did that. That's this expression here.
Oh, okay.
So what we said is the volume enclosed by this cylinder is pi r squared times L. And then we plug that in right here. Yeah. Anything else? Anything at all? Okay. So I'm gonna get back to this page later, because we'll work out the next part of this, but I just want to show you on the slide what we have so far. So when we applied Gauss's law to the first surface here, we found that the E field inside of the cylinder, which is where we are currently, is rho times r divided by 2 epsilon naught. So it basically just linearly increases with distance. There's 0 E field right at the center, and it gets bigger as you go out from the center with a linear dependence on distance. Okay? So now we're going to pick the next surface, which is surface number 2, and it's the same thing but outside. Okay, so now it's outside of our charge distribution, and as you can hopefully see a pattern emerging here, we don't have to do a whole lot of additional work to get the answer to this one, because we've done a lot of it already. The only thing that's really changed between these two surfaces is the enclosed charge. Okay, with the first surface, we're only enclosing some of the overall charge, right? But with the second surface, we're enclosing the whole thing. That's what's changed. And so someone back here said what that really amounts to in our equations, but what do we change in our equations? So the radius that we plug in to get our total enclosed charge is going to be big R, because we're trying to say we're enclosing the whole thing and not just some fraction of it, okay? That's what changes. But other than that, it's pretty much the same game as before. Make sense? Okay, so let's go back to the pen and paper stuff. All right, so surface number 2, which is our cylinder, where small r is now greater than big R. So now what we're doing is enclosing all charge out to radius big R. That is, we're enclosing all of the charge that's actually on the cylinder. So if we just take a look back here at the way we approached Q enclosed before, we said Q enclosed is equal to rho times pi times some radius squared times L. So what's changed is now this radius is big R. Does that make sense? So we have rho pi big R squared times L. That's now what we're enclosing with this new surface. All right? So we'll take Gauss's law once again, which says integral E dot dA equals the enclosed charge divided by epsilon naught, and we'll put in what we know. E dot dA integral works out the same way because of the type of symmetry we have. So that's E times 2 pi small r times L. That equals our enclosed charge, which is rho times pi times big R, that's squared, times L. And then we divide epsilon naught, right? Because there's an epsilon naught on the bottom there. All right, so how do we simplify this? Factor of pi cancels out just like before. Factor of L cancels out just like before. And then we'll just divide 2r and put it down here. Okay? So we have rho times big R squared divided by 2 epsilon naught times small r. Okay, and I just want to point something out about this. So like, these are just a bunch of constants. We have rho, we have big R squared, and then 2 epsilon naught, right? What is the actual dependence here on distance? It's 1 over distance. Okay, it's 1 over R, dependence. So what this is telling us is now that we're outside of the charge distribution, as we get further and further from the center, the E field gets weaker and weaker. But it's not an inverse square law, okay? It's just a 1 over r type thing. There's not an r squared on the bottom. Because of the different type of geometry, that factor, or that power of r works out differently, okay? Any questions? All right. So to summarize, here's what we have. Rho times big R squared over 2 epsilon naught small r. And by the way, I'm not going to go through this algebra right now. You can show this on your own. But if I just make some small substitutions, I can rewrite this to say lambda over 2 pi epsilon naught r. It's the same 1 over r dependence, it's just a different way of writing the constants. So you can make this step. And it's useful to see that because as long as we're outside of the charge distribution, it's behaving just like a line charge, right? Because this is the formula we arrived at for a line of charge. So I want to make a parallel to something we saw before, right? For spherically symmetric distributions, when we were outside, they behave just like point charges, okay? For cylindrically symmetric distributions, as long as we're outside, they behave just like line charges. And that's just a general thing we keep seeing with these sorts of examples. It's that 1 over r dependence. Okay. Any questions on this and how we got here? So let's graph it. So the E field, so now we're taking a different view of the cylinder. Now we're kind of looking at it face on. And we'll see the E field lines radiating out from the cylinder in all directions. It has that cylindrical symmetry. And what we see is we have these two different expressions. One applies for the inside of the cylinder and the other applies for the outside as far as what the strength of the E field is. We already derived these, so hopefully you already have this written down, right? Let's just think about what the graph looks like. Okay, on the inside, we have some constants and then multiplying r. Okay, so that means there's a linear dependence of the E field on distance. So it looks just like a straight line when we plot it to start off. But then, once we're outside, there's a 1 over r sort of thing going on. And if we were to plot what that looks like, it looks something like this. It's a curve that's getting smaller and smaller as r gets bigger. So the peak of the E field is right on the edge of the cylinder because it grows at first and then it falls off afterwards. Okay? So that's sort of a general thing we keep seeing in these examples. Any questions? Okay, so we'll keep it moving. All right, we've seen a whole bunch of examples with spherical symmetry and also some examples with cylindrical symmetry. So the last type of symmetry, as I mentioned, is planar symmetry. Now, I can really only think of one example here. It's just an infinite plane of charge. You know, they're all kind of the same in that regard. So let's define some of the parameters we're going to be dealing with here. So this is an infinite plane of charge. Obviously, I can only show you a small piece of the overall plane, but just imagine it extends infinitely far in all directions, okay? And then also note that even though in the real world we don't have infinite planes of charge, as long as you are dealing with a very large plane of charge that you're staying relatively close to, this result will still apply. So it's still a useful result. So for example, in a capacitor, this is going to be a useful result. Okay, how do we characterize the charge on the plane? So we're going to use a surface charge density. It's a charge per unit area, in this case, that we care about, right? So if you recall, charge per unit area is given by sigma. That's what we call our surface charge density. So we're going to go through this whole process of using Gauss's law to calculate what is the E field for this plane of charge, okay? And do you remember we did this example in the past, right? That was a pretty complicated example. It took a long time to get to the result. This is going to be a much simpler route to get the answer, okay? So rather than the brute force integral method, this is going to be a much simpler route today. So let's start by putting the E field lines right on the diagram. Can anyone remind me what generally they should look like? Let's say the plane has positive charge, just to put something on the page. What direction are my E field lines pointing? So I see people doing this, and that's right? They're pointing away from the plane of charge. If it has positive charge, they're just pointing directly away from the plane, and that's just happening everywhere along the plane. That's E. Make sense? Okay, so the next thing I have to do whenever I'm applying Gauss's law, I get a sense of what the E field looks like. We did that. Now I need to choose some kind of surface that I can actually apply Gauss's law to. Okay, and when we had a sphere, we said we're going to use a spherical surface. When we said we had a cylinder, we used a cylindrical surface. What do I do now? So I can't just use a plane. This doesn't work because this is not a closed surface. Gauss's law only works if you have a closed surface. Yeah, so maybe some kind of box would work. Some kind of box that is, at least enclosing some of the charge on the plane. There's actually a lot of different options for how you draw this figure. What I'm going to show you is a cylinder, but it could just as easily be like a rectangular prism, like you said. The point is, it extends and goes through the plane like this, and it has some kind of cross-sectional area. I'm just happening to show that the cross-sectional area is a circle, but it could work with any kind of cross-sectional area. Okay? So that's our Gaussian surface. Now, we have to be careful about how we take the next few steps, right? In Gauss's law, one thing we care about is the electric flux going through that surface. And that means, the E field lines piercing through the surface. If I were to take this overall surface and break it into three parts, like the two end caps and then the curved part, which one of those actually has some field lines going through it? Just the end caps. It's actually now the curved part that we can completely ignore in terms of flux calculation because there are no E field lines going through it, just through the end caps. Does that make sense? Okay, so let's go through it then on the paper. So start with the picture. I have this cylindrical shape, and I have E field lines going through both end caps. So here's an E field line going out this way, and then here's an E field line going out this way. But notably, I have no flux through this part. Okay, so let's number each part. Let's say the end cap on the left side, I'll call that 1. The end cap on the right side, I'll call that 2. The curved part, I'll call that 2. And then the end cap on the right side, I'll call that 3. So if I were to take integral E dot dA for this entire surface, I could break it into these three parts, right? So it'd be integral E dot dA for my first part plus integral E dot dA for my second part, and then for my third part. But what I'm doing here is I'm saying that second part has 0 electric flux. So we can cross that out right away. Okay? And the other two parts, it's pretty much the same formula that we're going to come up with. I hope you see that. Doesn't matter which side of the plane we're on, the flux through each of those end caps will be the same. So actually, let's work that out. So the nice thing about the situation we have here is if we look at the dA vector, let's say for the first part, it's also pointing straight out from the end cap. So it's pointing in the same direction as E. And if I do that for this part right here, same deal. It's pointing straight out from the end cap. So in both cases, I have an E field that's just going exactly in the same direction as my dA vector. Okay? Does that make sense? So here, let's just do some side work. E dot dA through one of these end caps. It's going to be E times dA times cosine of 0, because these two vectors are pointing in the same direction. And also, E is going to be uniform over the end cap, right? So like whether I'm talking about this point, or that point, E takes on the same value at all those points, right? So it's something that can be pulled out of the integral. And we'll just have E times integral over all my dA elements, which is just E times the total area of that end cap. Okay, so just to be clear, when I say A, I'm referring to this cross-sectional area right here. Does that make sense? But we have two of those. So overall, for my total flux, I have 2E times A. Okay? I pick up the factor of 2 just by including both end caps. Does that make sense? Okay, so what about my Q enclosed? So let's say this right here is where I'm actually intersecting with the plane of charge, okay? This is going to help me think about what my Q enclosed is. It's basically however much charge is contained in that specific area A. Does that make sense? I'm enclosing as much charge as you see on this area A. So the way I'll get at this is to remember that my surface charge density sigma is defined as charge per unit area, right? That's what this thing means. So the charge I'm enclosing is Q enclosed. The area taken up by that charge is A. So therefore, Q enclosed could be written as just sigma times A to rearrange this formula. It's just saying the charge is surface charge density times area. Make sense? So let's put this all together, right? We have our electric flux, we have our Q enclosed. So now we can put it together in Gauss's law to say integral E dot dA equals Q enclosed divided by epsilon naught. For my integral E dot dA, I get 2 EA, where again, A is just the cross-sectional area. For Q enclosed, I have sigma times A, and then I'm dividing out epsilon naught. So what happens? Cancel out a factor of A, here and here. I'm trying to solve for E. I want to know how strong the E field is next to this plane of charge. So what I get is E equals sigma divided by 2 epsilon naught. Does that look familiar? That's what we found earlier as an expression for the electric field close to a plane of charge. Okay? And it works equally well if we assume the plane is infinite. And again, this is not to say this is the easiest thing in the world to do, but compared to what we did earlier with brute force integration, this is a little simpler. Okay?
So it doesn't rely on how much area there is of the plane?
No. So, I mean, in fact, we're imagining the entire plane has an infinite extent to it. It just matters how dense the charge is packed on the plane. It depends on what sigma is. So if you have a really big charge density, a lot of charge very closely packed onto the area of the plane, you'll get a very large E field. If it's spread out and it's very sparse, you'll get a small E field. That's what this is telling us. Anything else? Back here?
That's right next to it.
So it turns out if the plane is infinite, let's go back to the picture here actually. If it's truly an infinite plane, and extends infinitely far, doesn't matter how far away you get from it, you'll still have that same E field strength. Okay, but if it's finite, then this expression is only valid if you're relatively close to it. Okay, and by relatively close, I mean your distance from the plane is small compared to the size of the plane. Okay. Okay, so then let's summarize. Magnitude E is sigma divided by 2 epsilon naught. And I'll just remind you, in the last chapter, not the last chapter, when we did Coulomb's law, we were able to arrive at the same result. Okay? So that's going to be all of the examples like this. We have a little bit more to do, but we've gone through all the examples that I wanted to see about how we use Gauss's law to calculate an E field. We've been doing that all day, basically. So you've seen all the types of symmetry that are going to pop up. So as long as you know how to deal with this case of a plane, the case of the cylinder, and the case of the sphere, you should be good to go. Any questions? Okay, so the last topic deals with conductors in electrostatic equilibrium. And hopefully this will answer any of those questions you had about, you know, how charge is spread out over a conductor versus a non-conductor. People are asking about this. Okay, so let's define some terms here. Does anyone know what I mean by electrostatic equilibrium?
With an equal amount of positive and negative charge.
Not necessarily that. What we mean in this case is nothing's moving around. Okay? If there is charge, it's not flowing in any particular direction. It's just staying put. Okay? So electrostatic equilibrium refers to any situation where there are no moving charges present. That's what we've been dealing with implicitly all the way up until this point, right? We have not really discussed what happens when you have, let's say, electrical current going through a wire. We're going to get to that later. So just keep in mind, we're always assuming in what follows that we're in electrostatic equilibrium, meaning no moving charges. Okay, so there's one thing that happens when you have a conductor in a state of electrostatic equilibrium. That is, the E field inside of that conductor is equal to 0. Okay, and it's pretty straightforward to see why that would be the case. All right, so imagine we have this conductor here, right? And it consists of, you know, a bunch of charges, some positive charges in the nuclei of the atoms, as well as some free electrons that can move around. Okay, so what would happen if I had an E field inside of the conductor? Maybe it was pointing this way. The free electrons in this conductor would be feeling a force from that E field, right? And what would that cause the electrons to do? It would cause them to start moving, right? But the assumption here is that nothing is moving. The only way that can happen is if there's no E field inside the conductor to push around the free electrons, okay? So as long as we're in electrostatic equilibrium, E is going to be equal to 0 inside a conductor. That's the only way that you won't have moving charges, okay? All right, so let's take a look at an example of this. Let's say we have a neutral conductor. This could just be like a sheet of foil sitting here. And then we take some external positive charge and we just put it close by. All right? So what I want to do is try to get a sense of how the E field inside the conductor is actually coming out to 0 in this case. Okay? Because you might imagine, you know, this charge over here is creating an E field. So, you know, how is it that it's 0 inside the conductor? That's what I want to get across. Okay? So what happens when we put a positive charge near this neutral conductor? What will the electrons want to do?
Move towards the positive charge.
Yeah, so they'll shift over, but that will be something that happens fairly quickly. They'll shift over. The electrons will now be over here. And what will that leave as far as the charge on the other side?
The positive charge.
Yeah, so if electrons are leaving this side and going towards this side becomes negative, this side becomes positive, right? This is what happens in the conductor, okay? Okay, so then if I were to ask what is the E field inside of the conductor? Just pick any random point inside the conductor. It's not as simple as just saying, what does the E field do to this charge, right? I'd have to add up the E field due to this charge, the negative charges on this side, and the positive charges on this side. I'd have to add all of those together to get the total E field, right? So let's say the point on the conductor where I want to calculate the E field is right here. Okay, so for the positive charge Q here, what direction is the E field that it's creating at this point? Yeah, so this charge is creating an E field going to the right, correct? Okay, what about these negative charges? Yeah, so that's going to create an E field going the other way. And then what about these positive charges? Also to the left. So if I want to see what the total E field is at that point, I'm going to add those together. So I'll call that EQ. That's from this positive charge here, going to the right. Call that E minus, going towards these negative charges that are building up on this side. And then I have E positive from these positive charges that have built up over here. So we're not going to go through this quantitatively, but you can show that these all will cancel out. You will get zero electric field. Okay, so that's just one example of how on the interior of the conductor you have zero electric field. Okay? And this is going to be true at any point you choose. Doesn't matter. These three electric fields, E negative, E positive, and EQ, are all going to cancel out and give you zero. Okay? And again, this is just one example. This is generally true of a conductor in electrostatic equilibrium. So any questions about this idea and this example of it that we went over? Okay. So we're going to keep moving. Another result that I want to show you is that if we have a conductor in electrostatic equilibrium, the net charge on the inside is always going to be equal to zero. And what that means is any charge that might exist on the conductor has to pretty much reside on the outer surface. Okay? And this is something that we saw in some previous examples. We had a conducting sphere. We said all the charge was on the outer surface. None of it was on the inside. I'm going to explain why that's the case. Okay? I'm going to explain why that was the thing. So we're going to start with the fact that if we have a conductor, that on the interior of it, E is going to be equal to zero. Okay, so we have zero electric field on the inside. And then what I'm going to do to figure out, what kind of charge am I dealing with on the inside is I'm going to bring in Gauss's law, okay? So what I'm going to do is draw a Gaussian surface. It's pretty much almost the same in terms of the shape as the conductor itself, but it's just a little bit smaller. So it's just barely on the inside of the conductor, just below the surface. Okay? Now, because the electric field is zero at every single point along this surface, what can I say about the electric flux going through the surface? Remember, electric flux has to do with E field lines going through the surface. Are there any E field lines going through this surface? There aren't, right? There's zero electric flux. Okay? So if we have this as our surface, we have zero electric flux through it because E is equal to zero, right? That's just automatic. If you have no electric field, you have no electric flux. There's no E field lines to go through the surface. So by Gauss's law, what I'm going to show you is that this implies that our surface that we drew is not enclosing any charge. Okay, that's pretty simple to show. Gauss's law says electric flux. So remember, I could write this as E dot dA, or I could just write it as phi. I'm talking about the same thing right here. That equals Q enclosed divided by epsilon naught. So if we're saying electric flux is equal to zero, automatically Q enclosed is equal to zero, right? But here's the thing. This surface that I drew, it's just below the surface of the conductor. It's just barely inside of it, right? So that means there's just no net charge on the inside of the conductor. if there is any net charge, it has to be on the exterior. It has to be on the outside. That's the only place it could possibly be, as we've shown. Okay, so to summarize, we have no electric flux through the surface, therefore we're enclosing no charge, and that is showing us that there's no charge on the interior of this conductor. That's generally true. There's nothing specific that we assumed here. Okay? So you have any questions on that? So that shows you why the charge has to be spread out on the exterior surface. Okay. Now, of course, if we're not in equilibrium, this is no longer going to be true. So if there are moving charges like a flowing current through the conductor, that's not going to be true anymore. But if there are no moving charges, this is going to be true. Okay? All right. There's one last fact that I want to derive here. And that is, okay, if there's no E field and there's no charge on the interior of a conductor that's in electrostatic equilibrium, could there be an E field just barely outside? And the answer is yes. We can figure out what that E field does look like, okay? So we have no E field on the inside, but just on the outside, we could potentially have an E field, okay? And we're going to derive what that E field looks like. So the first thing I'm going to claim here is that if we have a conductor and it's in electrostatic equilibrium, this E field just on the outside has to point perpendicular to the surface. Okay, so it has to point straight out perpendicular to the surface. And the reason for that is the following. Okay, so let's imagine we have some charge sitting here on the outside of our conductor, maybe just a free electron. Okay, and let's say the E field doesn't point this way, but it points like parallel to the surface, right? Maybe it points down. What would that do to an electron on the surface? It would start to accelerate along the surface, right? So that can't happen because we're assuming nothing is moving. So the only way you could have no charges moving is for the E field to be pointing perpendicular to the surface, okay? Otherwise, again, we'd be accelerating charge around the surface. So the next thing we want to do is not just say the E field is pointing in this direction, but try to come up with some kind of formula for what the E field might be, okay? And for this, we're going to once again use Gauss's law. So we're going to take our conductor with an E field that's perpendicular to the surface just on the outside, and we're going to draw a Gaussian surface. And this is kind of like what we did for the plane of charge, by the way. It's just a cylinder with cross-sectional area A, but notice how I'm placing the cylinder. The right half of it is on the outside of the conductor, and the left is on the inside of the conductor.
So if it's the same as the plane, there wouldn't be two, it would just be one for like end cap.
Yeah, right. So now, exactly. We're only going to consider flux through this one end cap. That's all that's going to come into play. Because, as we said, there's no E field on the inside, so we only have flux through this part, which is on the outside. Okay? All right. So let's do a little bit of math. The electric flux is equal to E dot dA. And we're going to do that over this entire surface. But when we break the surface into little pieces, what we see is this end cap has zero flux. So that's what this zero represents. Okay? And then the curved part also has zero flux. There are no E field lines going through that. So that flux is zero. And then if we work out the flux through this part, it just comes down to E times A. And I showed how that works before, so I'm just going to use that. Okay? So the total flux is just E, whatever the E field is here, times A, the area that we've chosen. Okay? Does that make sense? That's the flux. What about Q enclosed? This is pretty similar to the last example, right? Because on the surface of the conductor, we might have some surface charge density. We might have some charge per unit area, correct? That's given by sigma. If I take sigma times A, that gives me the total charge enclosed by this little Gaussian surface that I drew. Okay. So let's put that all together in Gauss's law. The total electric flux, which is E dot dA, is equal to Q enclosed divided by epsilon naught. So basically, I'm putting this in for the electric flux, I'm putting this in for the Q enclosed. And here's what we end up with. On the left side, we have E times A. On the right side, we have sigma times A divided by epsilon naught. Cancel out an A factor on both sides. And we get this. E is equal to sigma divided by epsilon naught just above the surface of a conductor. Okay? So really doesn't matter what kind of conductor you have, whatever the shape might be. We know that the E field just above the surface must be pointing perpendicular to the surface, and the strength of the E field is given by this. Okay? Remember, there's only one parameter this depends on. Epsilon naught is just a constant. So just depends on sigma. Just depends on how densely packed the charge is right above that point you're looking at. The more densely packed the charge is on the surface, the stronger the E field will be. Make sense?
And this is only true if there's electrostatic equilibrium?
Yeah, so everything we've just been saying so far assumes we're in electrostatic equilibrium, okay? So we're not going to get to what happens when the charges are moving around until it's going to take a little while. 2 more chapters, okay? But we'll get there. So with that said, here's an example that we can try out. Okay, so now that we kind of understand how to apply Gauss's law to these cases of electrostatic equilibrium, let's take a look at this example. So here we have a point charge, which I'm calling small q, which is 50 microcoulombs, and it's at the center of a shell. So this is a spherical shell. It has like an inner radius and an outer radius, and then just some empty space in the middle, okay? This conductor has 0 net charge. So the total charge on it is 0. However, we might have some charge building up like on this inner surface as well as on this outer surface. The only thing that matters is that when we add those 2 charges together, we get 0 for the total, okay? So the questions are, what are those 2 charges? What is the charge that builds up on this inner surface? And what is the charge that builds up on this outer surface, knowing that they have to add to 0? Okay? So we get the idea behind this? Let's work it out. So I'm just going to copy down the picture. We have a point charge, positive Q sitting at the center. And then we have our spherical shell. That looks something like this. Okay, and we're told that on this interior wall, basically, we might have some charge building up. And on this exterior wall, we also might have some charge building up. Again, as long as we don't have any charge on the interior, that's fine. We can have some on this surface here and this surface here, just not on the inside. Okay? So what I'm going to do next is I'm going to draw a Gaussian surface. So this is an imaginary surface, and it's right on the interior of the shell. Okay, so that's my Gaussian surface. All right. So what can I say about the E field at the location of my Gaussian surface? Well, it's on the inside of a conductor, and we're in electrostatic equilibrium. So basically, E is equal to 0 at the location of my Gaussian surface. Does that make sense? Yeah? Okay, so for this Gaussian surface that I drew, if I were to take E dot dA, what would I get? I get 0, right? I mean, there's just literally no E field. So there are no E field lines going through the surface, right? That has to be true. So my electric flux through the surface is 0. Okay? But what does Gauss's law say? Gauss's law says the integral over my surface of E dot dA equals Q enclosed divided by epsilon naught. So if this is 0, what do I say about Q enclosed then? It's also equal to 0, isn't it? In other words, because I have no electric flux through that surface, I know for sure that it's not enclosing any charge. Okay? But here's the thing about Q enclosed. That really consists of two parts, right? It's the positive point charge in the middle. I'm enclosing that for sure. But I'm also enclosing whatever charge is building up on this inner wall. So I can write Q enclosed as the sum of my point charge at the center and the charge that builds up on the inner wall, Q in. Does that make sense? Because that's the total of what I'm enclosing. So that means the charge building up on the inner wall is minus what this point charge is, basically. So minus 50 microcoulombs. Okay? So there's an equal but opposite amount of charge building up on this wall compared to what's in the center. Okay? Okay, but how do I find out what Q out is? So I figured out that this is minus 50 microcoulombs. How do I figure out what's building up on the outer surface?
What did you do the answer from like the previous example?
We choose a surface outside.
Well, here, we're going to use the fact that the net charge on the conductor is 0, right? So that means whatever charge is on this inner wall plus whatever charge is on this outer wall is equal to 0. Okay? So the charge on the outer wall is negative the charge on inner wall. So minus negative 50 is positive 50 microcoulombs. So what we're saying is the total amount of charge on the conductor is 0, but we have a negative charge building up on this part and a positive charge building up on this part, which add up to 0. Okay? We were able to figure out exactly how that works using Gauss's law. So do we have any questions on this example? No?
For this particular one, it doesn't matter at all how big that shell is or how far away it is from.
Yeah, so nothing we did here depends on that whatsoever. Yeah. Anything else? Okay, so I have one more example, but I think we're out of time. So you can take a look at this later and do it for practice. It's kind of similar to what we just did. We try to figure out on a conductor how much charge is building up on the different surfaces, but we'll just leave it here for today. And next week, we're going to start a new chapter on electric potential, which you might also know as voltage. So we'll get to that next week.